This is Electrostatics Lecture 1. In this lecture, we're going to talk about electric forces. We're also going to talk about some basics of electricity, which we did cover before when we talked about the photoelectric effect. We did talk about some of these things, but we're going to go over them again here because they're certainly applicable and they're worth saying again. So, to start out with electrostatics or electricity in general, we need to understand what a charge is. And there's more than one way to define a charge, but this is the way I like to define it. You can certainly look somewhere else and find a more technical definition and probably a more accurate definition, but I think this works well, and I'll explain why that is in my mind. I define charge as an excess or shortage of electrons. The symbol for charge is unfortunately Q. C is already used for other things, but sometimes it's a large Q, sometimes it's a little q, but we do use Q as the symbol. And the units are coulombs. Coulombs are the last of the fundamental units, which we talked about, I want to say, like the first day of school. Right? The other fundamental units that we have are mass, length, and time. And in my class, we always use kilograms, meters, and seconds. And the fourth fundamental unit is coulombs, how we measure charge. So coulombs does not break down to kilograms, meters, and seconds. It's its own unit. And we're going to see it showing up in a lot of other things. So that's what we're talking about. So now I call it an excess or shortage of electrons for a reason, because we tend to move around electrons is what tends to happen. Matter of fact, it's very easy to move around electrons. In chemistry class, you saw that with ionic and covalent bond, and electrons, get dropped from this atom, and another atom picks up that, or they share an electron, right? So this idea of moving electrons around is a very common thing. It's a very possible thing. So that's why I talk about it as an excess or shortage of electrons. The other thing that we could do is try and move around protons, but that's much harder, right? As we were talking about with nuclear physics, if we move around protons, we're changing the element. So does it happen in certain types of decay? Sure it does, right? But that's really the only situation where we see that we readily see protons leaving a nucleus. The vast majority of elements are stable. Protons don't leave or come in, right? And for us to try and make that happen is a very hard process. So when we're talking about electricity, we are talking about moving electrons around. So with that said, in this picture, we have an atom. It's got 3 protons. It's got 3 electrons. So this would be an example of a charge of 0. This would be 0 charge. Now, I don't want to say it's 0 coulombs. It is in this case, but I'm just going to say it has a charge of 0, and we're going to see what we mean about that in a moment. So this is something with no charge. Now, if I look at something else and I remove 2 electrons from this atom, and removing 2 electrons is not a super hard thing to do. We do it all the time when you squirm around in a plastic chair and then you got static buildup, right? You're either adding or removing electrons from your body. And that's just a quick example, but it's something that happens readily. So this is an example where there's still the 3 protons, because we're not going to get rid of protons or add protons from this atom. It's too hard, but we can remove a couple of electrons. So now there's a shortage of electrons. I have 3 protons. I have 1 electron. These are positively charged. Plus 3, minus 1. There's a charge of plus 2. Now here I don't want to say it's plus 2 coulombs, because it's not. We'll get into coulombs in a second. We're just pointing out that this has a charge of plus 2. It has 2 more protons than electrons, is really all we're saying right now. This would be a charge of minus 1, because what did we do? Again, we didn't change the number of protons, but we did have 4 electrons. So plus 3 minus 4, negative 1. So with that said, what does that mean to have a charge of plus 2 or a charge of negative 1? Well, this is what we're talking about. It's a relative charge. Now, important number to know, the charge of a proton, 1.6 times 10 to the negative 19, or really in my class we tend to use 1.602 times 10 to the negative 19 coulombs. And the charge of an electron is the exact same thing, except negative, right? Now, we know they're both the same. A proton and electron have the same charge, and they have exactly the same charge, except one is positive, one is negative. Now, what that means, I don't know for sure, right? I don't know, but it's a big important fact, right? That they both happen to have the exact same opposite charge, right? The same magnitude, opposite charge, right? Why is that? No one really knows for sure, but they do, and that's got to mean something. If we look at their masses, protons and neutrons extremely big, an electron tiny compared to those, right? Neutrons are neutral, +1, -1, and then what does that equal? Well, in coulombs, that's what it equals. And then we have the mass. Again, drastic differences in mass. So let me ask a question. Oh, hold on. I'm going to pause. All right, so let me ask a question. Let's get this thing out of the way. There we go. An object has a charge of -1 coulombs. How many extra electrons are there? Now, first of all, I can't ask the question, how many electrons are in this object? We have no idea, right? Because charge can only tell us how many more or how many less we have, right? So I don't know how much masses have or anything else about it. All I know is how many more electrons, or only thing I can ask is how many extra electrons are there. And I ask this question because the answer to this question, we don't need to memorize the answer to this question, but we need to understand what we're saying when we have a number like this. It's not outrageous for something to have a charge of -1 coulombs. We talked a little bit about current flow before. We're going to get into it in much more detail later. But it's certainly reasonable, like in my classroom, it's certainly reasonable to have about 1 coulomb of charge flowing through the light bulbs every second. When you start your car, there's a lot more than that. There's 4 or 5 coulombs of charge flowing through your car to start it every second. Or if you have a truck, it's like 7 or 8 coulombs every second. So these numbers, while a coulomb of charge is not a small amount, it's a reasonable amount. It's not something that's impossible. So when we start measuring things and we talk about, okay, that has 5 coulombs of charge. This has even, -0.3 coulombs of charge. What are we talking about? Well, we're talking about an excess or shortage of electrons. So if we had something that was -1 coulombs, how many extra electrons are there? I wouldn't mind if you paused and thought about this and tried to get the number yourself before I unveil it, but it's a unit analysis question. We know that we have -1 coulombs of charge, and we also know that there is -1.6 times 10 to the -19 coulombs per electron. So those are the two things, and those are the only two things that we need to know. So if you want to pause it and figure it out, that's great. Obviously, I can't tell, but I hope you at least give it a shot first. All right, so how many electrons does that work out to be? Well, it's -1 coulombs divided by 1.602 times 10 to the -19 coulombs per electron. We would see coulombs cancel out, and we'd be left with this number, 6.24 times 10 to the 18 extra electrons, which is this many, right? So what is that? Well, that works out to be hundreds, thousands, millions, billions, trillions, quintillions, and then quadrillion. I think it's that's the way it goes. 6 quadrillion, 240 quintillions, right? It's a huge, huge number. And it's important not to memorize this number, though I will say, not a bad idea to know this number because you're going to be using it so much that, nothing wrong with looking it up. You don't have to memorize constants, but it's a good one to have handy. So I never need you to memorize this one, but understand that if we talk about something that has a charge of -1, or even if it's, minus -0.1 or plus 0.0003, we're still talking about huge numbers of electrons that have to be moved around to build up these amounts of charges, right? So we're always talking about a gigantic number of electrons. So we don't record it by electrons because these numbers are just way too big to work with, right? So we measure it in coulombs. All right, so we've talked about how to build charge by moving electrons around. We've also talked about how many electrons it would take to build up some type of reasonable amount of charge. And all this is important because of the phenomenon of electricity, which is like charges repel and opposite charges attract. So kind of like when we talked about gravity before and we said, here's gravity and here's how it works, but we really don't know why it works. It holds true for this too, right? We know exactly how it works. We know how to harness these forces of electricity. We know how to make electricity do all these things for us. So we understand a ton about it. But why do like charges repel each other? We don't really know. And why do unlike charges attract each other? Again, these are things that people are still trying to study. And it really comes down to we don't really even know why electrons have a negative charge that's equal to the positive charge of protons, right? We don't know what happens. Um, Obviously, there's people out there that know more than I do about why or have theories why, and they certainly know more. But these are things that are fully established, right? What's the mechanism that allows these two charges to seed each other in order to push on each other, right? They're not touching each other. So there's some questions, but we still know this to be true, and we know a ton on how to deal with these forces. So, and that's what we're talking. We're talking about forces. If these two charges are repelling each other, that means they're pushing away from each other, right? If these two are pulling each other, same type of thing. That's a force. Forces are any push or pull. So when we talk about what electricity does, we're talking about forces. Electrostatic forces, if we want to calculate how much charge or how much of a push or pull there is, this is what we're talking about. And we have an equation for that, which is the electrical force or electrostatic force equals K, which is a constant. And unfortunately, I left the 9 off, but I drew it in later. Right? K is 9 times 10 to the 9 newtons, meter squared per coulomb squared. So it's K times Q1 times Q2 divided by R squared. Now, just to say it, this is not too different than the equation for the force of gravity. If you remember, the force of gravity was equal to some constant, which we call G, the mass of the first times the mass of the second, all divided by the distance squared. Again, another clue as to how these types of things work. The equation for electrostatic forces is extremely similar to the equation for gravity. They both have to do with what's attracted. This time it's charges, this time it's mass. They both have a constant, and they're both divided by the distance squared. Right? So a lot of similarities between these two equations. Now, one big difference, though, is that electrostatic forces can have a force of repulsion. There could be a push away, or there could be a force of attraction. There can be a pull towards, right? And this is the first one where the forces can be towards each other or away from each other, depending on the setup. So we know light charges repel each other. So these two would have a force that they would push away. And if we look at the math, and actually we'll start with the top one. I know that unlike charges attract. So a positive charge and a negative charge attract each other. But let's look at the math. K is a positive, it's just what it is. R, the distance between the two, that's always going to be a positive. So this is always going to be positive. This is always going to be positive. And then let's say that we have these two charges, one positive, one negative. Well, Q1's positive, Q2's negative, and I don't even care what the numbers are. If I put numbers in this way, I would get a negative force because I have a positive number, a positive number, a positive number, and then I got a negative number. So that negative number is going to turn everything negative. If I look at the second one, well, Q1, there we go, Q1 is negative, Q2 is negative. If I multiply all of this out, I'm getting a positive force. This is a force of repulsion. We know that they're like charges and they're supposed to repel each other. Mathematically, when I multiply them or I plug them in, I'm going to get a positive value. If I look at the last one, it's two positive charges. Again, I'm expecting repulsion. And this is a positive charge, and this is a positive charge. So everything in the equation is a positive charge. Again, I'm going to get a force of repulsion. So sometimes for these forces, I expect a positive answer. Sometimes for these forces, I expect a negative answer. And that's important because when we dealt with forces before, we had positives and negatives, but before they were telling us something completely different than they're telling us now. So I'm hoping you're following what I'm saying. What does this mean? Well, electrostatic forces are forces. Forces are vectors. There's a direction associated with those. But the positive or negatives that we get don't necessarily tell us up, down, left, and right like they did with other forces. This is important to understand. If I get a positive answer, then I am talking about a force of repulsion. Right? I get a positive answer when they're both negative. I get a positive answer when they're both positive. Both cases, that's repulsion. So if I plug in numbers and I get a positive answer, I know the charges are going to repel each other. If I get a negative answer, then I know it's a force of attraction, which means they're going to pull each other towards each other. That doesn't tell me the direction up, down, left, or right. I have to look at the system, I have to look at the question and determine what that means, right? So someone always says when they do the first problem, say, oh, it's negative, that means down. No, it's negative, that means they're attracted. Could be up, could be down, could be left, could be right, could be anything. You got to look at the situation and see what that means, right? Same thing when you get a positive, right? That means they're going to be repelling each other. So that doesn't mean the direction is positive. It means they're repelling, which means you got to look at the situation. Let's do an example. All right, so I know I've got the math right there, but here I have a square. Each side of the square is 2.5 centimeters. Draw that in. So I have 4 charges, and they are all spaced out in this square shape pattern. So 2.5 here, 2.5 here, 2.5 here, 2.5 here. It's a square. And at the corners of this square are these charges. All these charges have the same magnitude, which is 3 times 10 to the negative 6. But some are positively charged, which is Q1 and Q3 are both positively charged. And then the other ones have the same magnitude, 3 times 10 to the negative 6, but they are negatively charged, which is Q4 up here and Q2 here. What are we looking for? We're looking for the force on charge 3, which is this one here. And I'm actually going to erase what I just started to draw so it doesn't get in my way. So here we go. So even before we look at the math, and the math is just plugging in numbers, right, into the equation, do unit analysis. Let's think about it for a second. I don't really care so much when I get positives and negatives in my math, and let me explain why. Because when I look at this situation, I know Q4 and Q3 are unlike charges, so there's a force of attraction. Now, all I really care about is charge 3, because that's what the question asked for, and I'm telling you this is 2.5 centimeters, right? So I know there's a force of attraction between these two, which means Q3 is going to be attracted to Q4, which means it's going to get pulled up. So even though when I multiply these two numbers together, I get a negative, negative doesn't mean down, right? It means there's attraction. And if this one is attracted to that one, it means it's getting pulled up. When I look at the forces between Q3 and Q2, again, it's actually the same number, so it's still this calculation. I'm still going to get a negative 129.6, which means, again, that's a force of attraction, which means Q3 will get pulled this way, right? So, again, I have to look at the situation, and I have to establish what direction that means on my own. So even though this is a negative 129.6, I'm not going to keep that negative because it doesn't make sense to my picture, right? It's getting pulled up, it's getting pulled to the right, which in the end are really positive numbers, right, in the framework that we tend to have. Now, Q1 and Q3 are both like charges, so that's a force of repulsion. When I do the math, I get a positive answer. Now, notice it's a little different. They both still, well, K is still the same. The charges are still the same in magnitude, but this distance between here and here, well, that's not 2.5 centimeters. I have to calculate what that is, right? And I could do that with Pythagorean theorem. I make a triangle out of this. This side is 2.5. This side is 2.5. A squared plus B squared equals C squared. And this works out to be 3.54 centimeters, which I have to convert to meters so that all my units work out, right? So before we get farther into these numbers, I know this is a force of repulsion, which means this is going to get pushed this way. And because it's a square, I even know that this angle is 45 degrees because it's going to get pushed directly away. Because it's a square, I know that that's 45 degrees. That's going to come in handy later. Doesn't help me just yet. All right, so when I look at the math, 9 times 10 to the 9 Newton meter squared per coulomb squared multiplied. I see my coulombs all cancel out. I see my meters all cancel out. I am left with newtons, so it's going to be 129.6 newtons pulling up and pulling to the right, because when I do either one of these, I'm using the exact same numbers. For the force between Q1 and Q3, well, it's still the same K value, it's still the same charges, though there's no negatives anymore, but this distance that I found works out to be 3.54 centimeters. Again, I have to be in meters, which gives me this force. So there are the forces. Now that doesn't give me the total force on charge 3. It allows me to calculate, right? I have to add these 3 vectors together. And now that I know the directions of everything, I can now establish what really is positive and what really is negative. I look at this. Well, between Q2 and Q3, which is right here, so between 2 and 3, I'm going to change the color on this because that kind of gets lost in there, right? There we go. 2 and 3, well, that was a pull to the right. So now I'm going to make it positive. Not because it's repulsion or not because it's attraction, because it's pulling to the right. Right? So I'm going to make that a positive one, and it doesn't pull up. The force between 4 and 3, right? I'm not saying anything drastically different than before. That's pulling up. So there is no horizontal component, but there's a vertical component. Again, I'm making it positive because now it's up, and I care about that. And then the one between 1 and 3 is a force of repulsion, which means it's getting pushed to the left, making it negative, and down, making it negative. 129.6 plus a negative 45.82 works out to be this. I'm doing the exact same numbers, so that means the net force to the right is 83.78. The net force down, or net force up, is 83.78. So I know it's pulling to the right. The net force is to the right and up, to the right and up. I know this angle is 45 still because both of those sides are the same. So my force turns out to be, I don't know if you could see it, but 118.5 newtons at 45 degrees. So there is a problem that shows the calculations. It shows how we use those calculations to establish direction. And to be honest with you, we don't need the plus or minus. We could just reason our way through it, right? And lots of times I don't really care if the equation gives me a plus or minus because I already know ahead of time what the directions are just by looking at it. So, okay, these are going to be pulling. These are going to be pushing, right? So I establish that. So when I get a negative in the equation, I just drop it, right? Until I have to figure out my chart to get the total force. Still have to add those vectors up. All right, so there is electrostatic forces. The next one will be electric fields.